My name is Divya Oberoi. I work at the NCRA, and today I'm going to talk to you about the radio sun. Okay, but before I get there, I wanted to talk to you a little bit about to give you my personal perspective about astronomy, and I think what got me into astronomy, right? What really excited me and continues to excite me about astronomy. So, so as you already know, for an astronomer, the only source of information is the light which we gather using our telescopes. Right, this is really faint amounts of light which falls on our instrument. Source of information which we have about the rest of the universe. It's a slightly outdated statement. These days, we also look at things apart from electromagnetic radiation, right? Neutrinos, gravitational waves. But let's go with just electromagnetic waves for the moment here. And you also have the limitation that you can only observe. You can't experiment in the sense of the word we use in our labs, that you hold various parameters constant and vary just one of them, and then you can deduce what the law of nature might be or law of physics might be for some particular thing, right? So there is one piece of rock we call home. That's where we are confined, and we can only wait for light to come to us. Our tools are these observations, plus the fact that we have already a pretty elaborate framework of laws of physics, and then uh, the art of logical deduction, as I call it, right? These are our primary tools. Now, because we are really trying to gather very tiny amounts of light, the telescopes we work with, they tend to be really marvelous feats of engineering, right? Nobody else shares these needs with with astronomers. So astronomers typically are at the forefront of technology in building these instruments which will gather these very faint signals and analyze them. So your job essentially is, or at least a large part of the job is, to measure these faint signals and characterize them with the highest accuracy possible. And to me, the work of figuring out what it is like at some very distant place in the universe, which we will never visit uh, personally, is a bit like detective work, right? You have some piece of evidence which has come via the light. You have your laws of physics which tell you what is possible, and now you must apply your logic or your art and science of logical deduction to figure out what all can we learn about that place from these observations which we have made. And over the years, we have learned such an enormous amount about our universe from just looking at these, I mean, minuscule amounts of light, really tiny amounts of light which come to Earth. You walk down into, say, any library or look at Wikipedia or whatever is your favorite source of information. You find volumes upon volumes of what we know about the universe just sitting here right at home, which is uh, which is that, say, when you look down upon the Earth from space, you don't see any boundaries of countries, you don't see any racial divisions, you don't see anything else apart from natural features, really. It is, for me, also a source of an important lesson in both unity and humility. We are such a tiny speck in this grand universe of ours. And if you're not already familiar with, I recommend you to Google the pale blue dot and read what it has to say. That really is a very beautiful way of saying what I'm trying to say here. Okay. 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 So now let's get to the sun, right? Sun, as you know, is our sort of parent star of the solar system. We owe our life to it. And the spectrum of light from a star, as you know, is very close to a black body spectrum, right? So in reality, it deviates from the black body spectrum because there are various other ionized elements in the atmosphere of the sun which absorb some of that radiation. But overall, you can still describe it as a black body spectrum to pretty good approximation. Okay, and for our own star, for our sun, the peak of the spectrum is, let me get my cursor, is at about 5,800 Kelvin. It lies in the visible range, in fact, in the yellow-green region of visible light. Okay. Just a little bit of reminder of something which you already know. The black body spectrum is given by the Planck's law, which I'm sure Dipankar would have covered in his radiative processes lectures. So the functional form or the expression is given here. And what this is telling you is the brightness in units of watts per meter square per hertz per steradian. You could express it either as a function of frequency, the expression on top, or in terms of wavelength, the expression at the bottom. In radio wavelengths, we are in the regime where this denominator here, h nu by kt, is much less than 1, right? And you can show that in this regime, the expression on top reduces to something like this, right? It becomes so-called Rayleigh-Jean's law, and it has a particularly simple form, which shows that this brightness temperature, or I've not yet introduced what brightness temperature is, but let me use the word anyway, or sorry, the radiation which you are going to receive is going to be just this kt by lambda squared. Now, because this expression is trying to characterize the radiation which you receive in terms of a black body, and the only characteristic of a black body really is its temperature, right? That's the only thing which you need to characterize a black body, like you saw in this particular figure. There's only one parameter which is parameterizing each of these curves, and that's the temperature. Okay. So this temperature which occurs here, or for that matter here, is referred to as the black body temperature or the brightness temperature. Okay. So a body at this particular temperature is going to give out radiation, which is going to be characterized by the Planck's law. In the radio wavelength regime, it will have this particularly simple form, and that's what you are going to get. So just by looking at this radiation, I can figure out what the temperature of this body is going to be if the emission mechanism is that of a black body, okay, or a thermal emission. Okay, fine. One more piece of reminder. I'm sure this is something you've heard before. The units used by radio astronomers to express the flux density of light which is incident on their telescopes is a Jansky, in honor of the person who discovered radio waves coming from outside the Earth. One Jansky is a really tiny amount of energy, 10 to the power minus 26 watts per meter square per hertz, right? The sun is a really strong source. So solar astronomers tend to use a slightly different unit. They call it a SFU, a solar flux unit, and one SFU is equal to 10,000 Jansky. Okay. Now, because the thing which you are receiving light from, right? If you go back to this expression, this Planck's law energy density, this is per steradian, right? So it is per unit of angular, per unit solid angle, how much light you are receiving. When you're characterizing a source, you are often characterizing either the whole of the source, so you must integrate over the whole of the solid angle given by the source. Or maybe you are using an imaging instrument, and your imaging instrument has a certain resolution, and that is what is being denoted by this beam here. Right? Let's say a radio telescope to look at a patch of the sky, it has a certain angular resolution. And once you average the brightness temperature inside that solid angle and put it in this Planck's law expression, that is how you would relate the flux density you have received to the average brightness temperature inside the region from where you have received this radiation. Okay. Okay, good. So let's get back to our the black body spectrum. So what I've done now is I've extended the solar spectrum down into the radio range. And radio range I'm calling starting from somewhere around 1 mm, going to longer wavelengths. And by the time you hit about 10 meters or so, our ionosphere becomes opaque to the radio waves. So I've stopped somewhere around there, right? So essentially this orange arrow marks the radio regime, which I'm going to roughly talk about. Now you can see immediately that at the peak here in whatever units we are using, the energy which you were receiving, the spectral radiant emittance was about 10 to the power 9. Okay. While by the time I hit this radio regime, I've dropped to something like 10 to the power minus 7. Okay, 17 orders of magnitude lower. As I keep going down by about, I hit a wavelength of 1 meter, I'm sitting at something like 25 orders of magnitude less energy as compared to what the sun is radiating at the peak of its spectrum. So you would already begin to wonder, why am I going to a regime or to a wavelength where the sun is hardly emitting anything, right? What is it that I can hope to learn by looking at the sun in this regime? And that's the question which I would like to try to answer as we go along. Okay. Okay, so what I've done now is that I've also plotted on this a few other lines in the Rayleigh-Jeans regime corresponding to different temperatures. So this one was the sun. This was at about 5,800 Kelvin. This next higher line is at about a million Kelvin. The one above that is at 10 to the power 9 or a billion Kelvin, and at 10 to the power 12 or a trillion Kelvin. Okay, so if you had a black body corresponding to this 10 to the power 6 or 9 or 12 Kelvin, these would be the Rayleigh-Jeans uh, regime corresponding to that, and that would be the radiation which you would get. At the bottom, I've also shown what the spectrum of the quiet sun would look like. And what I'm calling active sun is a sort of envelope of emission from the active sun. It's not that when the sun becomes active, the emission becomes this. It is that it can rise. It doesn't rise at all the wavelengths at the same time. But when it rises, it can occupy, the peaks can hit as high as what I have shown here. Okay. Okay, so this is quite amazing. The sun, which we know is a black body at about 6,000 Kelvin, begins to approach a temperature of a million Kelvin when you look at it at wavelengths of about 1 meter or so. Okay, and the active sun is another more than 3-4 orders of magnitude brighter than that. Actually, hit no, sorry, much more than that, hit, coming to temperatures of almost 10 to the power 11 Kelvin. Okay, so let's see how does that come about. Okay. So to do that, we need to take closer look at the atmosphere of the sun, which we call the corona. Okay. What you have on your screen is a picture of the sun taken during a total eclipse. There's a little bit of cheating that the image which you see at the center was taken just after the eclipse and was sort of put in there. And what you immediately see, then I should also say that this is a heavily processed image. Okay, a lot of things have been done in terms of image processing to bring out the features which you see in there. And what are the features which you see? These are really faint lines along which the emission seems to be stronger, right? And if you ever played with a bar magnet and iron filings, you would immediately recognize that this seems like the field corresponding to a bar magnet, right? There's maybe a north pole and a south pole, and you have a lot of these magnetic fields. And these magnetic fields come actually in variety of shapes and length scales and so on. But hang on, we can't see magnetic field, right? So naturally it can't be the magnetic field which you are seeing. It must be something else. So it must be something else which is helping us see these magnetic fields. And in the case of the corona, what it is really the electrons which are trapped in along this magnetic field, and they are reflecting the sunlight. So the sun is illuminating this plasma, that plasma, and coming towards us. And that is what we are able to see. The places where you have higher electron densities are the places where you have more light coming towards us. And the places where you have lower electron density are the comparatively darker places. And because under such conditions, when you have, like I showed you, that the temperature at meter wavelengths here is about a million Kelvin, and I'll get to that in just a moment. Or actually, let me do that right now. So what we have established from the earlier picture is that all of this region is filled with magnetic field and with plasma. Okay. Now let's take another look or a more detailed look at what that plasma is like. So on the x-axis here is height above the photospheric uh, surface, and this thick or the solid curve here is the temperature. Okay, which on the left scale. So the region just above the photosphere is what is called the chromosphere, which is about 1,000 kilometers or so thick. And suddenly, just after that, there's a very narrow region called the transition region in which the temperature of the plasma increases by more than 1,000-fold, right? It's starting from around 10 to the power 4 here. Sorry, not 1,000-fold, 100-fold. Starting from about 10 to the power 4 here and hitting about 10 to the power 6 here. And beyond that is what is called the corona, and which is the plasma at a million Kelvin, the radiation from which is actually making that black body curve rise above the nominal black body of 5,800 Kelvin. Okay. And correspondingly, this dashed curve talks about the density of the corona, and you would see that it drops actually quite rapidly from in the chromospheric region, and then in the coronal region, it has a shallower decline. Okay, so this region, the corona, which surrounding the sun, is basically once you're above couple of thousand kilometers above the photosphere, it's full of plasma at a temperature of about a million Kelvin, and it is full of magnetic field. And this is really what makes the sun very interesting at radio waves, both the magnetic field as well as the high temperature plasma. By the way, the fact that this corona is at a temperature of a million Kelvin is still a puzzle. It's referred to as the coronal heating problem. It's a puzzle because we know that the photosphere is at whatever 5800 Kelvin. We also know that the source of energy, which is heating up the corona, must come from within the sun. So it has to cross at some point this boundary of 5800 Kelvin. But we also know that heat always flows from hotter bodies to cooler bodies. So how come energy is being transported from something at 5800 to something at a million Kelvin and keeping it there? And this is something I will come to again later in my talk. Fine, we have plasma, which is at about a million Kelvin. What kind of radiation do we expect from this plasma? That, again, I'm sure you heard a little bit about in an earlier talk. What you expect is the so-called thermal radiation, also known by the name Bremsstrahlung, right? So what is happening here is that you have a soup of plasma, right? Protons and electrons primarily in the case of corona. And as these electrons are being scattered by the ions or protons or helium nuclei, they experience a force which makes them undergo some acceleration, and accelerated particles radiate, and it is this radiation which is referred to as the thermal radiation. And as you can imagine, this depends on essentially parameters related to the density of the plasma, because it depends on how many collisions take place, or how close did the electron pass to the ion. And it also depends on what is the temperature of this, because a faster moving ion will spend less time, a faster moving electron, sorry, will spend less time in the vicinity of an ion which is exerting force on that, right? So the amount of radiation which you are going to be able to receive from a plasma can be characterized in units of, or in terms of, something called optical depth. Okay, the expression for which is right here at the bottom. Okay, it's referred to as tau. For a black body, the optical depth is much larger than one, essentially infinity. Okay, uh, as it happens for the corona, the optical depth lies in a very interesting regime. You can imagine that if the optical depth is a very tiny number, much less than one, the medium is essentially transparent. You just don't see it. If it is much larger than one, it has become a black body. For the case of solar corona, it so happens that at the radio wavelengths, or around meter wavelengths or so, the optical depth lies in a significant fraction of unity. Okay, so it's neither too low to be ignored nor too high to be simplified, and that actually makes life quite interesting. So it is this increase in optical depth as a function of frequency as you're going down this curve. Huh? So actually, I should have said as a function of wavelength as you're going down this curve, which is giving rise to this part of the spectrum. This is what is giving rise to the corona turning from essentially a transparent medium at these higher frequencies or lower wavelengths to a comparatively opaque medium, or a medium which is becoming increasingly more visible as you are going to meter wavelengths and beyond. Okay, so now let's also look at what kind of information can we get out of this thermal radiation. So as you saw in the expression which I had earlier, in the numerator was ne squared and in the denominator was t to the power 3 by 2. So naturally, you are going to be able to learn about the electron density distribution as well as the electron temperature distribution. Now, if you look at the figure on the left, what it shows you is the typical ray path of, let's say, an electromagnetic wave at 200 megahertz as it is traversing this corona. Right? In an earlier slide, I had showed you that there is a enormous density gradient in the corona, and once you are above the transition region, it's falling roughly as 1 upon r squared or so. And because of this density gradient, and because of the fact that the refractive index of this plasma at the radio frequencies has now become significant, rather than just traveling in straight lines, this radio light actually bends. It's something you're probably familiar with if you've seen mirages, right, on the Earth. So something similar is happening here because the density gradient, because of the nature of the density gradient, these rays tend to bend away from the sun, as I've shown here. So which means that actually for every frequency, there is a distance of closest approach, which you are going to have. And because the density is falling rapidly as a function of radius, and the tau is proportional to squared of the density, whatever you are going to be measured is going to be heavily weighted by what the emission which is coming from this, the surface of closest approach at any given frequency. Which means that if I dial my frequency knob up and down, I can move this distance of closest approach to a lower or higher height. I go to higher frequencies, I can probe deeper. I go to lower frequencies, I rise above in the solar atmosphere. So using this, I can sort of peel the layers of this onion and get information of the electron density and electron temperatures at a range of coronal heights. And I should mention that this is actually quite hard to get by any other means. Okay. Now, there's one more thing which you can, one more piece of information which you can get out of this thermal radiation, which I have not talked about earlier, which is that you can get an average magnetic field along the line of sight. That's for those of you who've done a course in plasma physics would probably recall that there is an ordinary and an extraordinary mode of propagation in magnetized plasma. And because of that, even the thermal unpolarized light picks up a very small degree of circular polarization. It's actually much less than 1%, around 0.2% or less at meter wavelengths. And if you can make this really sensitive measurement, then you can figure out an average magnetic field along the line of sight on the sun. And again, there is no other known way of doing it. Okay, so here is an sort of illustration of the radio advantage which we presently have. So the picture, the background picture you've already seen, this circle at 1.3 solar radii, it represents the typical field of view of the current generation of extreme UV and X-ray instruments, right? By the time you move out of this 1.3 solar radii, the emission measure of the radiation is so small that our current instruments are no longer able to detect it. The outer circle at 2 solar radii represents the uh, occultation disk of the most successful coronagraph we have right now. So what's a coronagraph? A coronagraph is an instrument which creates an artificial solar eclipse by blocking out the sunlight. And then you can see the faint light which is being scattered in your direction by the coronal electrons, right? Just the way we are able to see it during an eclipse time. So this region from 1.3 to 2 solar radii, we are actually not able to observe right now. Okay. However, radio waves, as I will also show you, or radio observations, I should say, as I'll show you later, not only we are able to see the full unobscured disk of the sun, we're also able to gather radiation or make images in this entire region out to 2 solar radii and beyond. So this gap in which we don't get information from any other means, the radio is a very good way of filling that gap. Fine. So far we've talked about the thermal emission. I had also marked an active sun part there, and those emissions, by very definition, come from a class of emission mechanisms which are collected together under the umbrella of non-thermal emissions. Okay. Now, these guys are all associated with solar activity, and what that means essentially is that they are going to take place close to the active regions. They are going to be some sorts of flares or bursts or storms, and they span a large range of times from fractions of seconds to even days. Okay. The emission mechanisms lie again can be divided into coherent and incoherent emission mechanisms. The incoherent emission mechanisms are gyrosynchrotron, or you've probably already learned a lot about synchrotron radiation. So this is just a cousin. It has relativistic electrons, but not as relativistic electrons as perhaps you have encountered in other aspects of radio astronomy. And these are this is the emission mechanism which is important for flares and coronal mass ejections. There is another one called gyro resonance, which is when the electrons are even less relativistic. Gammas might be just a factor of few. And then the emission spectrum is peaked at some harmonic of the gyro frequency, which I'm using the symbol nu b for. And typically this is the radiation which you see at a few gigahertz in the vicinity of active regions. There's another very interesting class of emission mechanisms called coherent emission mechanisms. And the one of interest to us is the so-called plasma emission mechanism. Now, what do you mean by coherent emission mechanism? That basically means that something is causing this emission to be, or different pieces of this emission to be in phase, right? It's like a laser beam in some sense, right? I can have a very tiny few milliwatt laser and I can light up a patch of wall across the classroom, right? Even though the light itself is very small, and if I had a simple led of the same wattage, it would be barely visible from the far end of the classroom. So that is the beauty of these guys, that even though the energy associated with the emission might be small, the observational signature can be very large because it is very high brightness temperature, and temperatures up to about 10 to the power 15 Kelvin have been observed. Because it's a coherent emission mechanism, it arises because of certain resonances that necessarily makes it comparatively narrow band. And because of the class of emission mechanisms involved, this emission peaks either at the local plasma frequency or its harmonic. What is the local plasma frequency? That's essentially the frequency, essentially the lowest frequency which can propagate in that medium without significant attenuation, and is proportional to square root of the electron density. And we'll talk just a little bit more about that as I go. Now, this plasma emission, it has many different bursts have this as the underlying emission mechanism, and it tends to have very elaborate structure in the time and frequency plane, and which is okay, not in this one, but in the next slide it will come. Okay, here is what I wanted to say about uh, the plasma emission, and actually other classes of emission also. Here is a very interesting plot which has on the x-axis the frequency at which you might expect emission from the sun. And there are these broad classes which are mentioned here. The gyro resonance and gyrosynchrotron are typically seen at a few gigahertz and above. This is thermal radiation, which is seen typically around a couple of gigahertz and below. And below about a gigahertz, you have this plasma emission, which is becoming increasingly dominant. Below about a few hundred, or no, many tens of megahertz, you have plasma emission, which is by far the dominant frequency. Because plasma emission is proportional to square root of electron density, it is actually a good proxy for the height above the solar surface if you have a good sense for a coronal electron density model, right? And that is what is shown here by this solid line, black line. And on the y-axis here is the height above the solar surface, okay, in units of solar radii. So you find that if this is the transition region, here is the corona, which is above that. And in the corona, it ranges from about maybe something like 500, 600 megahertz or so, and goes down all the way to very low frequencies. Okay, so this is also related to this distance of closest approach, which I was talking about, right? This really is happening at the place where the uh, the observing frequency has become the plasma frequency. Okay, that is the greatest depth which you can probe. Okay, how do you observe the sun in radio? Well, naturally, you have either spectrographs, right, which are basically either single dishes or just log periodic dipole arrays or something like that, which can give you the flux density as a function of time and frequency. And I'll show you an example in just a few slides. And it's what is referred to as a dynamic spectrum. And because this is the intake through the beam of that instrument, it really has no ability to tell you anything about the morphology of this emission or where did it take place on the sun or anything like that. If you want to get that information, you have to go to an interferometer. And interferometer is something which is going to be able to make for you an image of the radio sun, right? So once you can make the images of the sun, you should really think of your image data as basically a four-dimensional data cube, where theta and phi are the two dimensions in the image plane, right? Time, t is the time, right? I can take a snapshot and I can run a movie. And this new refers to frequency, which is that actually my movie is going to look very different depending on the frequency at which I choose to make it. So not only I have to make a movie in time, I have to make many different movies at different frequencies, and that is really what my data should look like. Okay, so I was talking about the different types of uh, solar radio bursts. All of these arise out of coherent emission mechanisms, and this is there's just time on the x-axis and the frequency on the y-axis, and the different shapes which you see here show the wide variety of solar bursts which we can observe. And I'm going to talk only about two of them. So one of them is called type 2 solar radio bursts. They are particularly interesting because they are driven by shocks which are associated with coronal mass ejections usually, as we will see a little bit later. But this is what a typical type 2 would look like in the frequency time plane, right? So they would last order 10 minutes, and they would start at higher frequencies and they would tend to sweep down to lower frequencies. If you and there is this upper envelope and or maybe an upper band and a lower band, right? So I told you that plasma emission mechanism comes or takes place at a fundamental and a harmonic. So this lower frequency corresponds to the fundamental, the higher frequency corresponds to the harmonic. If you look at it closely, you can maybe see that the fundamental itself is broken into two bands. The harmonic itself is, maybe you could imagine it to be broken into two bands. And that is because the place where the shock front is, there is a shock which is going forward and there's a shock which is going back. And the current understanding is that this emission is taking place at the forward and reverse shock corresponding to both the fundamental and the harmonic. How is it related to the CMEs? That's roughly something like this. So here is an image from a coronagraph, right? So this is the circle, the occulting disk, which is hiding the sun at the this disk represents the optical sun. And here is the coronal mass ejection, which we are seeing. Uh, as this shock is moving through this corona, it is leading to pileup of the matter ahead of it. And that is what is giving rise to this leading edge. This sort of darker material here is what is believed to be this magnetic flux rope which is sitting here, and this bright material again here is supposed to be the cooler uh, plasma which is being ejected out by the sun. Okay, so the place where this type 2 emission is coming from is somewhere here. Okay, at the head of this shock, where this uh, at the head of this magnetic flux rope where this shock front is sitting. And as you can imagine that as this shock is progressing higher and higher up in the solar corona, it is encountering medium of lower and lower density, right? And because our emission mechanism gives rise to emission at the local plasma frequency, the frequency at which you expect to see this emission should drop, right? And that is exactly what you, sorry, okay, I can't go back, but I can show you this slide. This also has a type 2 emission, which shows the emission starting at higher frequencies and going to lower frequencies as the time progresses. Okay. Uh, yeah, that's all I wanted to say here. Okay. So this figure gives you not just shows you not just a type 2 emission, which is what you see here. This is probably a better example of fundamental here and harmonic here, the two bands of the fundamental and the two bands of the harmonic. And a bit earlier than streaks of radio light, right, which are what are referred to as type 3 bursts. Okay, these are the most frequent bursts which we tend to encounter in the solar atmosphere or in the solar corona. And our belief is that they are actually arising from electron beams, which have been accelerated to something like a third of the speed of light. They're also very bright. In terms of Janskis, they can be of order mega Jansky. I should have said, in terms of Janskis, the type 2 emissions could be giga Jansky. Okay, these guys are now relativistic beams which are zipping through the corona. They are still being confined by the coronal magnetic fields, right? But they are moving at 0.3 the speed of light. Yeah, so they drift very rapidly in the frequency, and that is what gives rise to this sort of vertical streak-like appearance. Now here, the higher frequencies are at the bottom and the lower frequencies are at the top. And so this is when the beam was closer to the sun. This is as it is moving out. And by the time it is here, the density is dropping so slowly that even at one third the speed of light, the rate at which it is, the frequency is sweeping becomes smaller. And here again, you expect emission at both fundamental and harmonic, though it is quite hard to see them both at the same time, just because of the very high sweep rate. Okay? This is a sort of illustration of the entire range of heights which was being covered by the type 3, which was shown here. So this is sitting at a few hundred megahertz here, and it has come down to something like a few hundred kilohertz by the time here. Okay, this wind waves is a space-based satellite which has a low radio frequency receiver. Okay, and by the time you are observing this at frequencies of something like a few hundred kilohertz, it has actually come to the vicinity of the Earth. Okay, that's where the plasma densities are low enough that the plasma frequency is order 100 kilohertz or so. So so somehow these electrons are accelerated here. Here is a magnetic field line along which these electron beams are going to travel, and all along they are going to be giving out this type 3 radiation, and the frequency is going to be sweeping down to lower and lower frequencies as you go further and further away from the sun. So starting at about something like 250 megahertz in the mid corona, dropping to around a megahertz in what we call the interplanetary space, and coming down to sort of tens of kilohertz by the time you are approaching Earth. So I said earlier in my talk actually that the sun looks very different at different frequencies, and here is an illustration of that. So these are images of the sun taken at the same time but at different frequencies, right? So the bottommost row is at 17 gigahertz, the middle one is at 5.7, and the uppermost one is at 410 megahertz or zero point 0.4 gigahertz. And you can clearly see that the sun looks quite dramatically different in appearance at these different frequencies. Let's say this middle one, this actually the bright regions here, they correspond quite closely to the locations of the active regions on the sun. Okay, but as you go to this higher image, now you find that the edge of the sun, for example, is no longer well defined, because this emission is actually coming from the corona, which is not sitting at the surface of the sun but rather above it. And because it's a structure whose density drops only slowly, it has a diffuse outline, unlike a sharp limb which you see at the top. You also notice that it has regions, dark regions, which you might call coronal holes, and it has bright regions. And you can also see that these are almost consecutive days, 25th, 27th, 28th, 29th of June. You can see this structure also rotate along with the sun, right, as days go by. Okay, so basically, without getting into the detail of what you're seeing, or the point I want to make is that different radio images are telling you about very different structures on the surface of the sun, or in the corona rather. Here is an illustration of how dynamic this solar emission can be. Y-axis again is frequency, but it's not a continuous span of frequencies. It is sort of broken down into 12 chunks, each of around 2.5 megahertz. So one centered at 80 megahertz, 90, 98, and so on, all the way till about 300 megahertz. On the y-axis is time, and the time resolution is half a second. Okay, and there's 5 minutes of data. And you find many sort of thin slivers of emission which are taking place all over, right? Some of them are such that maybe you can see them all the way from around 150 to almost around 190 megahertz. There are others which are much shorter lived, that you see them in just 1 2.5 megahertz stretch, but don't see them just above or just below, right? There are many such examples which you will find. All of these guys, which are narrow in spectral range and short-lived in time, these are all different kinds of non-thermal emissions. And as we are building more and more sensitive telescopes, we are realizing that there are many, many more of these, or they're far more prevalent than we had once imagined. And these data come from a telescope by the name Murchison Wide Field Array. Okay? Another very interesting thing about this particular instrument is that it's actually an imaging instrument. It's an interferometer. And if I was to make, so what that means really is that for every pixel on this dynamic spectrum, I can make an image. Okay? And because you can see that things change quite dramatically across time as well as across frequency, it would actually make sense to image it at high time and frequency resolution. If I was really to image every single pixel in this, I'll get almost 500,000 images. And this is just 5 minutes of data. So what this is an illustration of a few different things. A, that the solar emission is highly variable in both time and frequency, and that our instruments are now getting there to be able to capture it, and also that it is going to be extremely compute intensive to be doing it, right? For 5 minutes of data, if I have to make 500,000 images, I am going to spend my lifetime just studying these 5 minutes of data. Another illustration of how dramatically different the quiet and active suns might look like. So on the right, the figure shows a radio map at about 240 megahertz of the quiet sun. And this dashed line is the optical sun. And you can see that the radio sun is actually much larger than that. In terms of brightness temperatures, you can see that this is roughly 4 times 10 to the power 5 is the peak. And there's not a whole lot of variation. By the time you're here, you've dropped to something like 2 times 10 to the power 5 Kelvin, right? And here is an image from an active sun taken during a type 2 burst. Okay. Here, if you notice the highest brightness temperature, this is now sitting at a little bit beyond 10 to the power 9 Kelvin. Okay. So 4 orders of magnitude brighter than the quiet sun. Okay. And this is a very impressive image. This is actually the highest dynamic range image of the active radio sun which has ever been made. This has an imaging dynamic range of greater than 10 to the power 5, which means that the the brightest peak, the contrast between the brightest peak and the noise in this image is greater than 10 to the power 5. By contrast, if you have a JPEG image, right, which we are all used to, it has 3 slices for RGB. Each of those slices has a maximum dynamic range of 256. Okay, and here we are talking about 10 to the power 5. Okay. Now, I had mentioned coronal mass ejections earlier, and here's a movie which shows actually a large number of them taking place during a particularly active time. Like I had said, that these are the most massive explosions in our solar system, and this is when these really energetic, high temperature, magnetized plasma is being thrown out from the sun. Now, if this happens to be coming towards the Earth, right, they can be launched in any direction whatsoever, but these are large in angular size. They can easily exceed something like 80, 90, 100 degrees in their angular extent. And so we are going to be hit by some of them. These are when they are directed towards Earth is what is when they give rise to what we now call space weather. Okay, what are the impacts of that? Well, the impacts range or uh, they have quite a large range, right? I mean, so for example, all the flights which say from India to US, which tend to go from close to the North Pole, they need to be diverted away because all this magnetized plasma, once it enters the Earth's magnetosphere, is going to be directed towards the North Pole and the South Pole because it's going to flow along the magnetic field lines. And you don't want your aircraft and people to be flying through that magnetized plasma, so you want to give a detour to those flights. Because it increases the atmospheric plasma density, it increases the atmospheric drag which our satellites feel. So their orbits decay faster. So their lifetimes become less, or you have to boost these orbits up, spending your precious fuel to do that. These days, we have astronauts living almost permanently in the space station, which was not designed to swim in a dense plasma cloud. So it creates issues for them. We lose lock on our GPS satellites, right? That's one of the reasons why you can't rely exclusively on GPS satellites for landing your aircraft. It gives rise to disruptions in the electricity grid because these big currents in the atmosphere give rise to induced currents in the ground, which uh, which imply that the assumption which our electricity grids make, that the ground is at a common potential everywhere, is no longer true. So it can give rise to actually all sorts of issues for our currently technology reliant society. In fact, in the risk register of some of the countries, it is among the highest risks which you have. Okay. So, but why am I telling you about all of this? Because it is possible that radio observations can one day give us the tools to be able to predict the impacts of this space weather. And let me tell you a little bit about how can we do that. Okay. So this is a slightly more technical slide, but I want you to really focus on this image here. And what I want you to notice is that, you see all these contours here. They map out the edge of the CME, which is seen in the white background light. And this yellow circle is the place from where these spectra have been taken. Okay, this is frequency along x-axis and flux density along y-axis. And I'd earlier mentioned that there is this gyrosynchrotron emission, which you can see from this energized plasma. And we are now able to see it and model it. And using that, we can actually predict the magnetic field inside these CMEs. Now, why that is important is because the space weather is crucially dependent on the magnetic field of these CMEs. Earth is surrounded by its magnetic blanket, the magnetosphere. If the magnetic field of the CME is sort of parallel to that of the magnetosphere, it just pushes against it and then goes by the sides. If, however, they are oppositely directed, then that magnetosphere, and that is when it is really dangerous. But for that, you need to have a sense for what is the magnetic field in the CME. This particular estimate is just an estimate of the vector magnetic field. What is the orientation of the magnetic field? Yeah, here is another and even more impressive example than the previous one, where we are able to detect these CMEs, these coronal mass ejections, these really faint emissions from the plasma at much further radii than has ever been done before, right? And to give you a sense for how much weak this signal is as compared to the peak here, this is less than one part in 10,000 of the signal which you see at the peak here. And this is again one less than one part in 1,000 of the signal which is there at the center. Okay. Now, where we really want to go with this is something along something which I'm trying to show here. This is something which we have not yet managed to do, but this is something which we are trying to do. So what you see there in the background is actually a true image of the sky. It's huge. You can see that it is almost 60 degrees along the side. That yellow dot here is actually where the sun was, which has been subtracted from these data. And now we can see all the background sources which are there in the sky, right? So this is like seeing stars during daytime, right? And what I've shown here by this cartoon, this sort of banana shaped thing, is a cartoon representation of a CME which is moving in some direction. Now imagine that the sky is full of sources which are giving rise to tiny amounts of this linearly polarized light. And as the CME is flying through ahead of these background sources, because of the magnetized plasma of this, the background linearly polarized light is going to change a little bit, right? Its plane of polarization is going to rotate. If I can make a large number of these measurements, then I can actually invert these data to figure out what is the vector magnetic field in this CME. And this is really the only known technique using which we can measure the vector magnetic fields of these CMEs. Once we are not only able to do it, but do it before the CME has actually hit the Earth. It takes roughly 2 to 4 days for it to travel the distance from the sun to the Earth. That would be fantastic. Then we would be able to predict space weather, which is a currently which we capability the capability for which we don't currently have, and that's going to have a huge societal impact as well. Okay. Okay. So is something I wanted to sort of mention as a key thing which radio astronomy can deliver for solar science and for society, and that's also something which we are working towards. The other aspect which I wanted to mention is another really cutting edge problem which we can address using using radio astronomy, is looking at the coronal heating problem. Right. So like I had said earlier, coronal heating problem is basically looking for an explanation for how come a 1,000,000 degree corona is sitting atop a photosphere, which is just 5,800 Kelvin. And basically, there is agreement in the community that the result to heat up the corona is the coronal magnetic field. Now the problem reduces to finding out mechanisms using which you could extract the energy from this magnetic field and turn this into heat. One of those is the so-called nanoflare hypothesis, which basically means that, look, there is this big tangled magnetic field all over the corona, which, like I had showed you in an earlier picture. And a magnetic field is a little bit like a rubber band. You can keep twisting and turning it and so on, and it's going to keep adding the stress, building the stress in that magnetic field. A rubber band is eventually going to break because it can't sustain more stress than some limit. A magnetic field can't really break. But what it can do is that it can undergo something called magnetic reconnection. It is going to look for opportunities to relax to a lower energy state by looking for places where oppositely directed magnetic field is coming close to each other, and then it is suddenly going to snap and reconnect, and all the energy which it is going to release is going to be used up in heating the plasma which is present at that place. And now you have managed to transfer the magnetic energy into thermal energy. That is what we are looking for. So we'd been looking for signatures of these nanoflares, as they are called, and only recently we had the first reliable detections of these features, which is what is shown here. So what is shown here essentially is a measure of uh, the energy content in these tiny bursts, which we have managed to measure. Right? It's a histogram, and on the x-axis is how strong they are. So this is milli SFUs, so milli solar flux units. So the things I want you to remember essentially from here are that these are the first detection that there are these nanoflares which are taking place, whose radio evidence we can see. This is much weaker. These flares are much weaker than had ever been seen before, at least a factor of 100 weaker than the next weakest flares which have been reported. We're very excited about these because they satisfy all the criteria for being relevant for coronal heating. There's a lot more to do before we can say that coronal heating is solved, but they provide beautiful evidence that nanoflare based coronal heating is at play. Okay, and here's a sort of Diwali card which a student of mine had made for me. Sorry, which is showing us these not quite these nanoflares, but these really tiny bursts which are happening all over the sun. This is a real movie. This is not a, or this is a movie based on real data, is a better way of saying it. So there are these sort of Diwali explosions happening all over the surface of the sun. Individually, they are too tiny, but collectively, they have enough energy to heat up the corona to a million Kelvin and sustain it at that temperature, because left to itself, it will cool. So you have to regularly keep supplying it heat to maintain it at that temperature. Okay. So with that, I just wanted to summarize and say that solar radio observations tell us about aspects of the sun about which we can't learn from any other observation. So these are primarily about coronal physics and primarily to do with releases of magnetic energy, right? And at least two key places where radio observations will play a very important role in improving our understanding and also being very useful, directly relevant for our society, are going to be space weather and coronal heating. And it's a very exciting time in solar radio physics right now because a large number of new generation instruments have become available comparatively recently, and they have really multiplied our ability to gather information about the sun. So we are really close to making big leaps in improving our understanding about solar and coronal physics. And with that, I'd like to, okay, here's a bunch of resources which you could look up. The first three are about solar physics. The radio astronomy, I'm sure many other people have already given you things about. Uh, of these, this is an ebook which is available, which for free download. The others are not easily available. Yeah, I mean they are available only as physical books, not as e-copies. Okay, so with that, I think I would like to thank you and take any questions. Yeah.
Hello, sir.
Yes, please go ahead. Yeah.
So, so I had a question that is, we thought that the emission happens at the plasma frequency and the harmonic, which is twice the plasma frequency. So my question is, why isn't emission seen at the higher harmonic?
So that is to do with the details of how this emission takes place. So the second harmonics comes about because of of combining of two waves which are propagating in opposite direction, and that tends to, their superposition tends to give rise to a wave which is at twice the harmonic, twice the fundamental. To go for the higher harmonics, you need a superposition of a larger number of these waves, and the probability for their happening is really low. So they are, so it's theoretically possible, but practically they have not yet been observed here.
Okay, sir. Thank you.
So I was just there is some research going on that Jupiter can be a a quite good solar mirror, but for extra emissions. That is, if we the Earth doesn't faces the sun constantly, it faces only the one side of the sun. But if there is solar activity happening on some other side, and that is Jupiter on that side, and there are actually some observations of extra emission from Jupiter which are in synchronous with the radio sun's emission. But I don't know whether it is applicable in the radio decline, or how is it helpful by taking
So,
observations from Jupiter.
anecdotally, I can tell you that at least once we have seen solar radio bursts reflected off the moon. So it was a time when the geometry was such that the sun was below the Earth's horizon, the moon was up, and we happened to be observing for a completely different reason. And we saw a burst which was very reminiscent in its frequency time structure of a solar burst. And it turned out that another observatory for which could actually see the sun at that time had seen a burst with very similar frequency time structure. So yes, it is. I don't know so much about Jupiter, but we know that we have seen observations of solar bursts reflected off the moon.
Hello, sir. Thank you for this amazing talk. So my question was, in most of the cases, CMEs are associated with strong solar flares. So is it possible that we can predict this CME on the basis of solar flare properties? Thank you.
Yes. So yeah, you're absolutely right. There is in fact a lot of work going on uh, in exactly that area. There are in fact two aspects to that. Because the CMEs are taking place because of an enormous buildup of magnetic energy in something, and suddenly then this energy exceeding some threshold and giving rise to an explosion. One thought is that why not look for buildup of these magnetic stresses and use that to predict the occurrence of CMEs. So while our capability to examine the buildup of magnetic fluxes is pretty decent, I would say. It has not yet managed to translate to a good prediction of the CMEs themselves. Okay. Then the other aspect you had is that, okay, why can't we look at a CME and use that to predict what kind of, why can't we look at a flare and use that to predict what kind of a CME it would give rise to? That again, we have not yet managed to do well because the CME undergoes very significant evolution within the first few solar radii, where it is interacting with comparatively dense corona which is overlying it. And depending on the magnetic structures which are pre-existing in that corona, its own configuration can change quite dramatically. But you're right that this is something which there is active research which is going on currently.
Dave, there is a question in the chat which is not quite to do with the radio sun, but Somya asks, how do you get 5,800 degrees Kelvin at the surface with over a million degrees K inside the sun? You want to take it up?
Sure, I can say something about that. So that's certainly a very valid question. Uh, so in the core of the sun, the temperature exceeds few tens of million Kelvin. That's where these nuclear reactions are going on. And from there, the gamma ray photons are being emitted, which come out to an outer layer. Uh, and these photons then sort of tend to random walk their way through to the next higher layer on the sun, which is referred to as the convection layer. And these layers are named simply because radiative layer and convection layers are so named simply because the most efficient process of transport of heat in these layers is respectively radiation and convection. So you should not think of the sun as a as as something at being a constant temperature. There is an enormous temperature gradient from the center of the sun out to the surface of the sun. Okay? It's only the core which is at these few tens of million kelvins. I don't have in my head the numbers for temperature for the radiation zone and the convection zone, but there is a fairly steady decline. And the top 30% of the sun, roughly, in terms of radius, is the so-called convective zone, where there is a big churning motion which is happening all along, where the fluid at the bottom is being heated because of the absorption of these high energy photons which are coming from bottom. As it becomes heated, it becomes buoyant and therefore rises to the sun and gives rise to the setting of these convection cells. And it is the temperature of the fluid which comes up to the top, which is at about 5800 Kelvin.
Hi Divya, there is a question from YouTube. Viren is asking, we know that the solar magnetic field is widely known. Can it be possible that major space missions which are going near the sun leave a stream of charged particle towards the sun?
Sorry, I'm not sure I understood that. The space missions which are going towards the sun, what do we want them to do here?
So which are going near the sun leave a stream of charged particle toward the sun. So he's asking.
So you want to shoot something, you want to shoot a stream of charged particles towards the sun. Okay. So the solar wind, so there is something called solar wind, which is basically the extension of the corona, which is again hot plasma. It's a plasma bath in which the Earth and in fact all of our planets are immersed. It's moving out from the sun at a speed of many hundred kilometers per second, roughly 300 to 400 kilometers per second in the equatorial belt, and much higher speeds outside the equatorial zone. So when some spacecraft is flying towards the sun, it is actually it is overcoming the resistance from all these particles of solar wind which are going out. So I'm not sure what the intent or the motivation behind the question that you can shoot something, shoot a beam of plasma into the sun. Uh, Sorry, I don't have a good handle on that. Yeah.
Yes, sir. So NASA just announced this Sunrise mission, wherein they're sending like 6 satellites to make a big telescope to like study the radio frequencies of the solar of the radio frequencies of the these emissions, coronal mass
Correct.
emissions.
Yeah.
It's basically so the premise says that it's basically to predict the space weather for better missions and everything. But I wasn't sure about how like how this would work out, since like we could always see the solar flare start and like the coronal mass ejection start from the light that is coming to us. So how does this like telescope benefit us?
Okay. So that's a good question indeed. So the Sunrise mission is essentially is a flying interferometer. It will have 6 spacecraft. I don't remember the configuration, but it is few tens of kilometers, I think, would be the separation between these spacecraft. And the idea is that you now have this flying interferometer using which you would be able to make images of whatever of the sun and whatever is coming from the sun towards us. So what, uh, as I had shown you in the movie about the CMEs, you are able to see the CMEs when they are close to the sun, right? Because that's when the plasma is dense enough for you to be able to see them. As they move further away from the sun, it becomes really hard for you to see them because it becomes very tenuous. Also, the CMEs which are coming towards the Earth, it turns out they are the ones which are hardest to see, because imagine this was the sun and a CME was going perpendicular to the Earth sun line. Then you have this entire structure of the CME through which you have to see the through which you have to trace your line of sight. And because of the project, much more electron density. If the CME was coming towards me and I have to trace my line of sight through this, I have really only a small piece of the CME to see through, which does not give me enough electron density. So coronagraphs are not very well suited for looking at CMEs which are coming towards the Earth. The sunrise is closer to a technological demonstrator than a mission which is actually going to solve the problem. This would be the first formation flying radio interferometer up there. So they will show, it will be more like a proof of principle to say that yes, we can fly this constellation, we can get these data on the ground, we can make images, and we can actually see the emission from the CME. Once you're able to do that, I think you will need to fly a much more sophisticated and much more detailed mission, and at a place which is not close to the Earth. It will probably be closer to L5 Lagrange point before it can meet the space weather objectives here.
Can I ask one question outside the?
Sure, sure.
What are the most challenging issues that needs to be resolved in the solar physics right now, which can be addressed through radio?
So there are. So I would count 2. One would be about coronal heating. where we are trying to make progress by looking at these really tiny radio flashes of light, trying to characterize them, and trying to see if we can find high energy counterparts of them, which will help us estimate the energy corresponding to them. Uh, the other, I guess, one could relate to space weather and say that if we are able to make I mean, if you are able to overcome, let's say, all the challenges of ionospheric calibration and so on, and detect these few millijanskis worth of polarized emission, say 10, 20 degrees away from the sun, with high enough SNR that we can invert them to figure out what the magnetic field of a CME is, that would be huge. That would have an enormous societal benefit. Yeah.